Alright guys, here's a problem on relative motion. It'll be real similar to how you're going to do the lab. And there's two possibilities. You could have, I'm going to do my fun circles. So you could have object 1 coming at object 2. And let's say the speed of v1 is 4 meters per second, and the speed of v2 is whatever you want it to be. Let's say, here, we'll keep it easy, 6 meters per second. And then typically with these problems, they'll give you the starting distance between them. They have to give you some other information. They could give you the time, they could give you the distance. In this case, let's say they are, let's say 10 meters apart, and they're coming at each other. And then the question typically is, well, how long until they meet? Let's call it time of contact. Time of contact. So there are two ways to approach this. I'm going to show you using relative motion. So we're going to solve with relative motion. There's a math way to solve it. Simultaneous equations, if you've heard the term. Solve with relative motion. Now, why isn't this, they gave us t, d, and v. Why can't we just do v equals d over t? So here's, block that off. That is the equation. I mean, it's a constant motion problem. There's no acceleration, so we should be using v equals d over t. The issue is they're going to meet. They're 10 meters apart. I don't know how far object 2 is going to go before it makes contact with object 1 because they're coming at each other. So there's no way. So what I would get, I have individual speeds. I don't know their distance, which means I can't solve for t using the just straightforward equation. So with relative motion though, I can take a step back and put myself, sorry guys, put myself in one of the cars. Let's see if this color comes up. I'm going to put myself in car 1. So there's my x. I'm in car 1. If I was in car 1, how fast would I measure you coming at me? Well, I would measure my own speed. So here I'm doing the relative motion I'm going to do in purple. I would measure my own speed as, well, I wouldn't, so it's 0 meters per second. And then I would measure the car coming at me, object 2, at 10 meters per second. And then from my perspective, object 2 is going to go 10 meters before it meets up with me. So we can come down here, well, what's v? It's really v relative, so it's 10. So if object 2 is coming at me at 10 and it goes 10 meters, I can solve this for t. Just take t to the other side. 10 divided by 10 is 1 second. We're going to meet in 1 second. I can do the same thing. Let's do another color. I can do the same problem from, what color is going to stand out? We'll do yellow. From object 2's perspective. This is going to get sloppy, but so from object 2's perspective, so that's all going to be yellow. Again, we're looking at relative motion. So from object 2's perspective, they're going 0 meters per second, and they would measure me coming at them at 10 meters per second. Well, the math's the same. I'd say 10 equals, so now I can go 10 meters before I intersect with them. That's how relative motion works. I can't say you're not moving and you can't say I'm not moving because we both measure 10 meters per second. Just from different frame of references. Now from outside frame of reference, I'm going 4, you're going 6. Then we would have to look at it with the simultaneous equations. But that's more a math thing that I don't want to focus on. If you want to see it, just let me know. But relative motion checks this off real quick. It's 1 meters per second. Now if I wanted to know, this would be a part B question. Here we'll go back to white. So a part B question would be, let's say, well, so how far does object 1 go before it meets? We know it takes 1 second for them to meet. So where does object 1 get to in 1 second? You would use object 1's speed, 4 meters per second. So for this one, you're going to get, again, v equals d over t because it's constant motion. This time you would use the 4 as the velocity. Distance you would leave out, and you'd put in 1 second. So d1's going to go 4 meters before it hits object 2 or makes contact with object 2. So how do you get object 2's distance? Well, you could plug in 6 instead of 4, and you get 6 meters. Or we know the total distance is 10 meters. You could subtract the 4 meters that object 1 goes and get 6 meters also. So it all works out that way. The only other thing that could happen, what if they're not coming at each other? I don't know how to add another page. All right, so the other option is, what did we just do? We came at each other. The other option, I'm just going to do this real quick, is that object 1 could be coming at object 2 and trying to overtake them or catch them. So let's do v2 as, here, we'll leave this as, well, here, we got to make v2 slower for v1 to catch it. So we'll make v2 4 meters per second, and we'll make v1 6 meters per second. I'm just making up numbers, but again, we can keep the distance the same, 10 meters. So now the question is, well, again, it's time. How long till contact? It's constant motion again. It's v equals d over t. But again, I don't know. We're 10 meters apart. So I have to overcome 10 meters, and then the other, whatever distance I need to catch up to you. So it's going to be more than 10 meters. So I don't know my distance, which means I can't solve v equals d over t just using me. Relative motion-wise, if I'm going 6 and you're going 4, so from my perspective again, so we'll use, again, relative motion. From my perspective, I would say I'm going 0 meters per second. And then and think about this, if you're walking by someone in the hallway, or driving's a little more noticeable. If you're going 60 and drive by somebody going at 50, you don't see them going 50. You drive by them at 10 miles per hour. You see 10 miles per hour. You would measure 10 miles per hour. This is the same thing. So we would do 6 minus 4. So object 2 from our frame of reference is really only going 2 meters per second. Again, from our frame of reference. From someone outside their car, they're going 4 meters per second. From frame of reference car 2, they're not moving, but I'm going at 2 meters per second. So that's what all the relative motion stuff means. So now I can say, well, if he's going 2 meters per second, well, I guess I wouldn't catch him. It might make more sense. Sorry, after I think about it. This will come out mathematically fine. I guess we're trying to calculate the time that I catch up to you. We flipped it, and it's the time that 2 catches up to me. Regardless, I guess if we want to make this more clear, we would actually want to say this is 0. v2 is 0 meters per second. Again, mathematically, it doesn't care. It doesn't matter, but I think the physics needs to make more sense. So from object 2's perspective, I would be going 2 meters per second. You get the same numbers. So then down here, I would say 2 equals 10 over t, and I would solve for t, which would be 10 divided by 5. I'm sorry, 10 divided by 2, which is 5 seconds. So it's going to take me 5 seconds to catch up to you. And then the question comes up, well, how far do you travel? Or how long does that take me? So if we're looking for D1, again, we go back to constant motion. It's v equals d over t. This time, though, I use my speed, my 6 meters per second. How far am I going to travel would be the 6 meters per second. So d is what we're looking for, d1 specifically, and t is 5 seconds. So I'd multiply both sides by 5. It's going to take me 30 meters to catch up to you.